Hello friends, good afternoon and welcome to EduSat Live Lectures. Dear friends, today in chemistry we will be continuing with our previous lecture on phenols. Today is the second lecture on phenols. In this lecture we will be talking about its acidity and its chemical reactions. To discuss this topic we have with us our subject expert Dr. Aparajita Chauhan. Dr. Chauhan is Associate Professor in Department of Chemistry in Sri Aurobindo College, University of Delhi. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome ma'am.
Thank you. We will take forward today's lecture from where we left last time. Last time we did the methods of preparation of phenols and some physical properties of phenol. Today we shall be discussing the reactions due to the cleavage of OH bond, that is the acidity of phenols, and then some reactions in which phenol acts as a nucleophile, that is acyl reaction, esterification reaction of phenol. This will be continued by electrophilic substitution reactions of phenol, followed by some special reactions of phenol. So to start with, if we talk of acidity of phenol, then we know that phenol ionizes to some extent in water to form phenoxide ion and the hydronium ion. So why is phenol acidic in nature? If we look into the resonating structures of phenol, then what we find is that in few of the structures oxygen has a positive charge, as a result of which this oxygen and hydrogen bond becomes weak and hydrogen is given off as proton very easily. Whereas if we look into the resonating structure of phenoxide ion, then what we find is that the negative charge is on electronegative oxygen in three structures, which is more stable. Hence we say that phenol is acidic in nature because the conjugate base of phenol, that is the phenoxide ion, is more stable as compared to phenol. Now if we talk of the effect of substituents on the acidity of phenol, then we know that the electron withdrawing substituents, if present at ortho and para positions to the phenoxy group, then they increase the acidity of phenol by delocalizing the negative charge by minus I effect as well as resonance effect, that is the minus R effect. So when these groups are present at ortho and para positions, so if I look into the acidity of nitrophenols, then what we find is that nitro group, when it is present at ortho and para positions, it stabilizes the phenoxide ion by pulling the electrons towards itself through minus I and minus R effect. What we mean here is that through minus I and minus R effect, the electrons will be delocalized further onto the oxygen of the nitro group, hence stabilizing the anion. Whereas if we look into the meta nitrophenol, then this nitro group cannot undergo conjugation with the phenoxy group and it stabilizes the carb anion only through minus I effect. As a result of this, what we find is the order of acidity is, or para is most acidic, followed by ortho and then the meta. Why is para more acidic as compared to ortho? If we look into the structure of orthonitrophenol, then what we find here is that there is chelation in this. There is intramolecular hydrogen bonding in orthonitrophenol, due to which the giving off of proton becomes little difficult, and hence the order of acidity is para-nitrophenol followed by orthonitrophenol and then meta-nitrophenol. Now if we look, we put more of nitro substituents on the ring, then what we find here is the number of the electron withdrawing groups as well as their relative position will affect the acidity. If they are present at meta position to the OH group, that is at 3 and 5 position, then since they are at meta position to OH, here the conjugation is not possible. And since conjugation is not possible, what we find here is it is stabilizing the phenoxide ion only because of minus I effect. Whereas if it is present at ortho and para positions to the OH, it stabilizes the phenoxide ion because of minus I effect as well as minus R effect. And this 2,4-dinitrophenol is more acidic as compared to 3,5-dinitrophenol. Now, if we place 3 nitro groups at ortho and para positions to OH group, then we find that this is most acidic because they will withdraw the electrons by minus I and minus R effect. So, what we know is that among nitrophenols, para-nitrophenol is most acidic, followed by ortho, meta and then phenol. And if we are putting the substituents, then depending on the position of the substituents, the acidity will be different. Now, let us look into chlorophenols. Here it is slightly different, that chlorophenols exert a plus R effect and a minus I effect. And second thing that we know is in case of halogens, minus I effect, the magnitude of minus I effect is greater than plus R effect. Hence, what happens here is we find the order of acidity is slightly different from nitrophenols. What we know here is that in case of these all the 3 compounds, it is the minus I effect which is stabilizing the anion because of it is withdrawing the electrons. Whereas, because of the plus R effect, when halogen is present at ortho and para positions, it is destabilizing this because it increases the electron density on the oxygen group. Now, in between these 3 compounds, that is the ortho, para and the meta, what we find is that orthochlorophenol is most acidic. Why is orthochlorophenol most acidic? Because in case of orthochlorophenol, the chloro group is nearer to OH group, as a result of which the minus I effect is most. This is followed by metachlorophenol and then the parachlorophenol, in which the magnitude of minus I effect is minimum. So, this is being stabilized by minus I effect and destabilized because of the plus R effect. So, what in general what we see is that if groups are exerting minus I and minus R effect, or the magnitude of minus I effect is stronger, then they increase the acidity of the substituted phenol. Whereas, if an electron donating group is present on the nucleus, then it increases the negative charge on phenoxyoxygen, making the release of proton more difficult. Secondly, the electron donating groups destabilize the anion because of the plus I effect and plus R effect also if they are present at ortho and para positions to the phenoxy group. So, what we find here is if we look into the acidity of methoxyphenols, then what we find is metamethoxyphenol is most acidic, followed by phenol, then orthomethoxyphenol and finally paramethoxyphenol. The reason being that in methoxy group, the magnitude of plus R effect is greater than minus I effect. So, when this group is present at meta position to the OH group, then it exerts only minus I effect, and as a result of this minus I effect, it stabilizes the conjugate base. Whereas, when this group is present at ortho and the para positions, then it destabilizes the conjugate base because of the plus R effect. It goes into conjugation and the electron density increases at the phenoxyoxygen. So, what we find here is that the base becomes strong. So, the conjugate acid is a weaker acid. Hence, the order of acidity is metamethoxyphenol followed by phenol, Metamethoxyphenol is more acidic because it is stabilizing the conjugate anion by -I effect, which is followed by ortho. In case of ortho, again here, since it is closer to the OH, the -I effect will be stronger, as well as we say because of the ortho effect, it is almost as acidic as phenol, then followed by the paramethoxyphenol. Now, if we look into crisols, then crisols are less acidic than phenol, whether it is ortho, para or meta, because we know that the effect of the methyl group is +I, and because of this +I, it destabilizes the conjugate base because of the +I effect, that is, it increases the electron density on oxygen. And secondly, when it is present at ortho and the para positions, it undergoes hyperconjugation, and because of this hyperconjugation effect, the electron density on phenoxyoxygen increases further, hence making it a stronger base, so the conjugate acid becomes weak. So, what we find in this case is that the order of acidity is phenol is most acidic, followed by metacrisol, then the paracrisol, and finally the orthocrisol, because in orthocrisol the magnitude of +I effect will be maximum because it is closer to the OH group, as well as because of the hyperconjugation it is least acidic. So, now if we look at an overall picture of this, then what we find is that electron donating groups will increase the acidity. So, what we find is, electron withdrawing groups will increase the acidity, that is what we find is nitro group, which has the maximum -I effect and -R effect, is most acidic, followed by chlorophenol, which exerts a -I, strong -I and a +R effect, but the overall effect is -I effect, due to which again it is more acidic than phenol. Then if we look into crisols and methoxyphenol, then what we find is that these are less acidic than phenol because of the +I effect of the methyl group as well as hyperconjugative effect, and in case of methoxy, it is the resonance effect which destabilizes the phenoxy ion. So, this was regarding the acidity of phenols. Now, we will look into reactions in which phenol acts as a nucleophile, or we will look into pheno-oxide ions which are acting as a nucleophile. So, what we see is, first thing that we have to concentrate on is that pheno-oxide is a stronger nucleophile as compared to phenol. So, what we find when we talk of acylation reaction, that is the ester formation, in this reaction what happens is phenol reacts with an acid halide or an anhydride in presence of pyridine to give a ester. So, what we find here is that in this reaction what is happening, it is an esterification reaction and phenol is acting as a nucleophile. When we do the acylation reaction, this is known as O-acylation reaction, and in this case phenol is acting as a nucleophile in presence of pyridine, because in this case acyl chloride, acid chloride is quite electrophilic and phenol can act as a nucleophile. So, what we find here is that it undergoes a special type of base catalyzed mechanism in which we call as nucleophilic acyl substitution reaction, and it occurs via addition elimination mechanism. It is different from normal nucleophilic substitution reactions which are given by alkyl halide. So, what we find here is, in this case pheno-oxide, if I talk of a base catalyzed reaction, then in case of base catalyzed reaction, phenol ionizes to give us a pheno-oxide ion, which then acts as a nucleophile and gives us an addition product with the acid halide or an anhydride. This is a tetrahedral intermediate which is unstable, and then what we find here is, since it is unstable, this will eliminate a halide ion to generate this product. So, what we find in this mechanism is that in this case OH is acting as a nucleophile and it reacts with a phenol, that is, we are doing the reaction in a basic medium, and it abstracts a proton to form a pheno-oxide ion. Now this phenoxide ion acts as a strong nucleophile, and in the second step it reacts with the carbon of the carbonyl group to give us a tetrahedral intermediate. And now this tetrahedral intermediate now loses a halide ion to regenerate a ester, which is the final ester product. Now if we look into the next reaction, which is Schotten-Baumann reaction, what happens in this reaction is that phenol reacts with benzoyl chloride to give us a phenyl benzoate. In this case, we are using sodium hydroxide as the base, because in this case phenol cannot act as a nucleophile, because in benzoyl chloride there is double bond between the CN oxygen. At the same time there is conjugation between the phenyl ring and the carbonyl ring, and this carbon is not electrophilic enough for the phenol to act as a nucleophile. So what happens is, first phenol ionizes to give us a phenoxide ion, which then acts as a nucleophile in presence of NaOH. Then the reaction is the same, that it reacts with the benzoyl chloride, giving us a tetrahedral intermedium through an addition reaction, which then eliminates chlorine to give us the final product. And this modification of esterification, which is benzylation, when we do in presence of sodium hydroxide, is known as Schotten-Baumann reaction. So here again what we have done is, we have shown you the mechanism where it is phenol is acting as a nucleophile, reacting with the carbonyl carbon, giving us a tetrahedral intermediate, from which the halide ion is eliminated to give us the final product. This is the mechanism of acylation reaction. So what we do is, now if we go into acid catalyzed esterification, the reaction mechanism is same, that is, it will involve the 4 steps. First, the formation of the tetrahedral intermediate, then the elimination of the halide ion to give us the final product. But this reaction is slightly different. What we find that when we are doing base catalysis, then in that case base is converting phenol into phenoxide ion, which is acting as a nucleophile. Whereas when we talk of an acid catalyzed esterification, here first what happens is, proton reacts with the oxygen of the carbonyl group, and what we get is a intermediate like this. So in this case what we find is that we have a positive charge on the oxygen, and then this positive charge, because of the resonance effect, the carbon has a full positive charge on it. Then in this case, now phenol acts as a nucleophile through the lone pair of electrons on oxygen here, and it reacts to give us this intermediate. Now in this intermediate a proton transfer takes place. This proton goes from here to here, and at the same time we get this second intermediate. In this case now what happens is, this HX is eliminated. At the same time this undergoes deprotonation to give us an ester. So this is acid catalyzed esterification reaction. So please remember, this reaction can follow 2 mechanisms, base catalyzed as well as acid catalyzed, and this is known as acyl nucleophilic substitution reactions, which involves first the addition and then the elimination. Similarly, the other reactions in which phenol can act as a nucleophile are Williamsons ether synthesis. We know that phenol is a weak nucleophile. So what we do is, we take phenol and we dissolve it in aqueous NaOH. When we do that, then it ionizes to give us a phenoxide ion. Now this phenoxide ion acts as a nucleophile here through this oxygen, and it undergoes SN2 mechanism. In this case we have to keep in mind that we have to take either unhindered primary alkyl halides or unhindered secondary alkyl halides, then only substitution reaction will take place. So here what happens is, SN2 mechanism takes place. This oxygen, this phenoxide attacks from the rear side on this carbon to give us phenolate, or it reacts with sodium phenoxide, reacts with methyl chloride to give us anisole. please keep this in mind that if instead of taking a primary alkyl halide or a secondary alkyl halide, we had taken tertiary alkyl halide, then in that case elimination would have been the major product, that elimination would have predominated and the alkene formed would have been the major product. So, these were the few nucleophilic substitution reactions of phenol, in which, not the nucleophilic substitution, the reactions in which phenoxide ion was acting as a nucleophile. In the next lecture, we will be discussing nucleophilic substitution reactions, and we will find that they take place under drastic conditions because the cleavage of CO bond is more difficult as compared to cleavage of OH bond. Now, today we will be taking typical reactions of phenol, few of the electrophilic substitution reactions of phenol. Now, when we talk of electrophilic substitution reactions of phenols, we know that the OH group is ortho and para directing group. It is a strongly ortho and para directing group. Why is it so? Because the lone pair of electrons on oxygen undergo delocalization with the phenyl ring and they increase the electron density at all the positions, that is at the ortho and the para positions. First, what we find is they will increase the density over the entire ring because of the strongly plus R effect, and more so at ortho and para positions because of the resonance effect. So, this ring is highly activated and it undergoes electrophilic substitution reactions under mild conditions. Second, what we find is that why does ortho and this substitution takes place at ortho and para positions. This is again a very important aspect. If we now look into the carbocations which are formed by an attack of an electrophile at the ortho position, then what we find here is that we have 4 resonating structures for this. And if we look into this structure is very stable or is the most stable structure, because in this structure each carbon has its octet complete. So, this contributes maximum towards the resonance. Similar is the case if the attack takes place at the para position, that if the electrophile comes and reacts at the para position. Here also what we are having is again one structure is more stable as compared to other structures because the octet of each carbon atom is complete. And what we find is this contributes again to the maximum towards the stability of the carbocation, which is the intermediate which is formed in the electrophilic substitution reactions. Whereas no such resonating structure is formed if the reaction takes place at the meta position. So, hence what we find is that the incoming groups, the electrophile will attack the benzene nucleus, the phenolic nucleus at ortho and para positions when the OH group is present on the benzene ring. So, OH group is highly activating. Not only that, it is also ortho and para directing because it stabilizes the intermediate carbocation formed because of resonance. So, now let us look into the few examples of electrophilic substitution reactions, which are halogenation, nitration, sulfonation, alkylation, and in alkylation we will be dealing with FRIEDEL-CRAFTS alkylation as well as acylation reactions. So, as I have already told you that phenol is highly activated towards electrophilic substitution reactions. So, we do not, in most of the cases, we do not need a catalyst to bring about this reaction. So, when we do bromination, what we find is that bromination is very reactive in polar solvents like bromine water. And second, the substitution takes place at all the available positions, that is ortho and para positions, resulting in a polysubstituted product. So, what we need to do is, if we want to prepare only ortho and the para products, then we will have to do the reaction under milder condition. That is, we will have to do the reaction in a non-polar solvent. In a non-polar solvent, like we will have to do the reaction with bromine in presence of CS2 or in presence of carbon tetrachloride at low temperature when we will get the mixture of ortho and para substituted products. So now the question arises, why when we are doing it in aqueous medium we are getting ortho and the para products, whereas we are getting a tri-substituted product, whereas when we do the reaction in presence of CS2 we are getting only ortho and para bromophenol. See, when we dissolve phenol in water, phenol ionizes to give a phenoxide ion. And this phenoxide ion, since it is more reactive than phenol, it reacts at a faster rate with bromine, resulting in formation of bromophenol. Hence, the equilibrium is disturbed and more of phenol is converted to phenoxide ion, which then reacts further with bromine. Then what we find is, after monobromination has taken place, the dibromination and the tribromination, that the second substitution and the third substitution, takes place at a faster rate because of the presence of the more electronegative bromine atom, which increases the ionization of phenol and the reaction takes place easily. Whereas, when we do the reaction in presence of CS2, then the ionization of phenol is suppressed and what we get is only ortho and the para bromophenols. So, now we will have to discuss nitration, and if we talk of nitration, then again what we find is, towards nitration also phenol is very reactive. Since it is reactive, what we find is that phenol, on reaction with dilute nitric acid and dilute sulfuric acid, it gives us a orthonitrophenol and paranitrophenol. But the reaction is fast, yield is low. Why is it so? Nitric acid is an oxidizing agent and it oxidizes phenol to parabenzoquinone. So, little phenol is left which undergoes nitration to give us paranitrophenol and orthonitrophenol. So, for this what we will have to do is, we will have to carry out the reaction in an alternative way. That is, first we will have to protect the group or deactivate the ring towards further substitution, that it does not react with nitric acid, and then do the reaction. So, what we find here is that due to high reactivity, when we treat phenol with nitric acid and sulfuric acid, concentrated nitric acid and sulfuric acid, the nitration takes place at all the three positions. And secondly, the reaction is fast, but the yield is low because, as I have said, that nitric acid will oxidize phenol to parabenzoquinone. We will be discussing this in detail after the break. Thank you. talking of nitration, so as I have told you that when we do the reaction with concentrated nitric acid and concentrated sulfuric acid, we get 2,4,6-trinitrophenol, which is picric acid, but the yield of the reaction is low. So what we do is we can use an alternative method to prepare this. So in this case what we do here is we will first do sulfonation with concentrated sulfuric acid. When we do sulfonation, then what happens is that this phenol is converted to ortho or hydroxybenzene sulfonic acid and para-hydroxybenzene sulfonic acid. Now in the second step, we do the reaction with concentrated nitric acid. When we do this, this nitric acid brings about desulfonation, that is, it will remove the sulfonic acid group and we get trinitro product, that is 2,4,6-trinitrophenol, which is also known as picric acid. So in this method we get a high yield of 2,4,6-trinitrophenol, in which first we have deactivated the ring towards further electrophilic substitution reactions, and since the lone pair of electrons are involved in delocalization, further due to presence of sulfonic acid, it does not undergo oxidation. So picric acid is a very important military explosive. It was initially used as a military explosive, and French used it as a bursting charge for shells under the name melinite. Later on, ammonium picrate was developed, which is a modern armor piercing shells due to its ability to withstand the severe shock of penetration before detonating. So it detonates later and penetrates first. This picric acid can also be used as an antiseptic as well as astringent, and the very important use of picric acid is that it is used to purify polynuclear hydrocarbons, that is, it forms addition compounds with them, that is picrates. These yellow colored picrates can then be separated by filtration. So if we have to prepare now orthonitrophenol and paranitrophenol, again we face the same problem, that is nitric acid acts as a oxidizing agent and it oxidizes phenol to benzoquinol. So what we do is first we convert phenol into nitrosophenol. This can be done by two ways. The first is the normal way that we do, that is the very popular method, that is by treating it with nitrous acid, that is reaction with NaNO2 and HCl, when in situ nitrosinium ion is prepared. Or what we can do is we can carry out the reaction with nitrogen trioxide when it acts as an ion, nitrosation ion, and it brings about the reaction. So first what we get is when we do the reaction with dinitrogen trioxide, it produces ortho and para nitrosophenols, and these ortho and nitrosophenols on reaction with dilute nitric acid are converted to orthonitrophenol and paranitrophenol. So what we've done in this reaction is first we brought about the nitrosation reaction, that is doing the reaction with NaNO2 and HCl when nitronium ion is prepared in situ, which then is oxidized by nitric acid. Now if we have to prepare metanitrophenol, then what we do is we start the reaction with benzene, convert benzene into metadinitrobenzene. Then this metadinitrobenzene is reduced with ammonium sulfide. This ammonium sulfide brings about selective, or we'll say partial reduction, when it reduces one of the nitro groups to an amino group. Now again we are doing that same reaction, that is we are doing the diazotization of amino group with HNO2 and HCl at 0 degrees Celsius when we get benzene disonium chloride salt. So, and then when we heat this benzene disonium chloride with warm water, we get metanitrophenol. So we can prepare orthonitrophenol, paranitrophenol and metanitrophenol first by orthonitrophenol, first by doing diazotization and then doing the further reaction whereas if we have to prepare the meta, then nitrophenol, then first we prepare the dinitro product and diazotization, followed by hydrolysis with warm water when we get meta-dinitrophenol. If we look into sulfonation, then we can bring about sulfonation of benzene with sulfuric acid. Then when we do the reaction at low temperature, then orthoisomer is the major product, and this reaction is non-reversible reaction, whereas when we do the reaction at high temperature, then para-isomer dominates, and this reaction is a reversible reaction. This reaction is an example of thermodynamic versus kinetic control. That is what we find here is, when we do the reaction at low temperature, then reaction proceeds via that mechanism which has low energy of activation, and hence the ortho product is the major product. Whereas when we do the reaction at high temperature, then the para product is formed, because we prefer a thermodynamically stable product, and that is the para product. So now if we heat the reaction mixture, then what we find is, if there is ortho has been formed in this reaction, that also converts to give us into a para product, because para product is thermodynamically more stable. So what we find is that when we do the reaction at low temperature, then in that case ortho product is the major product, whereas when we do the reaction at high temperature, then the para product is the major product. Now when we talk of FRIEDEL-CRAFTS alkylation, then phenol behaves little differently as compared to benzene. It does not give a high yield in FRIEDEL-CRAFTS alkylation or acylation. The reason being that the AlCl3, which we know we use to generate the electrophile, in this case reacts with lone pair of electrons on oxygen to form a complex, and this complex is, hence this AlCl3, which was supposed to generate the electrophile, fails to do so. So, and what happens here is that from this complex HCl is eliminated and we get a chloroaluminium salt. We can bring about this reaction if we do the reaction with excess of aluminium chloride. Then in that case it undergoes alkylation and we are able to get ortho and para alkyl phenols. Another interesting example is that if we take metacresol and we do the reaction with propene in presence of aluminium trichloride. So we can use other alkylating agents also. Instead of alkyl halides and AlCl3, we can also use alkenes and alcohols and alkylating agents in presence of sulfuric acid, in which case the problem of complex formation will be eliminated. So when we do this reaction, then what we find is that this propene generates a secondary carbocation, which is isopropyl carbocation, and then this isopropyl carbocation attacks at ortho position to OH group. Now we know that this OH is more activating as compared to methyl group. So, and these two groups are reinforcing each other, that is methyl, this is para to methyl, whereas this position is ortho to OH, and the substitution takes place here, resulting in formation of thymol. And we know that thymol is present in oil of thyme, and it can act as an antiseptic, antifungal, antibacterial, hence it is used in mouthwashes. Another very useful method in which we get high yield of alkylation is when we do the reaction of phenol with tertiary alcohols in presence of concentrated sulfuric acid. When we do the reaction in presence of concentrated sulfuric acid, this reacts with tertiary butyl alcohol to generate a tertiary carbocation. And now this tertiary carbocation reacts as an electrophile, it reacts at the para position to the OH group, resulting in formation of para tertiary butyl phenol, and we get quite high yield, which is 80% here. So what we find in case of phenols, the better alkylating agents are alkenes in presence of sulfuric acid or alcohols in presence of sulfuric acid instead of alkyl halides with AlCl3 because AlCl3 fails to generate the electrophile. Now, if we talk of FRIEDEL-CRAFTS acylation, then we get a very poor yield that of ortho and para hydroxyphenols because direct acylation is not a very good method. Again, what we find here is that this AlCl3 reacts with O here and fails to generate the electrophile. Now, before I proceed further, I want to make one point very clear here. That is when we do the reaction with AlCl3, that is a reaction of acyl halide, acid halide with AlCl3, then what happens is then C acylation takes place. That is, this is an example of electrophilic substitution reaction. Whereas when we do the reaction of phenol with acid chloride in presence of NaOH or pyridine, then please remember then esterification is taking place, that is O acylation is taking place, that is the reaction is taking place at oxygen. Whereas when we do the reaction in presence of AlCl3, reaction is taking place at carbon here. When we do the reaction in presence of a base, that is NaOH or pyridine, then acylation is taking place at oxygen, that is O acylation is taking place. So one has to keep in mind that if they give us complete the following reaction and the catalyst is AlCl3, then C acylation will take place, and if the catalyst is pyridine or NaOH, then O, that is esterification, will take place. Now we will talk of special reactions of phenolic compounds. So what we found in this reaction was the previous reaction, that if we wanted to prepare orthohydroxyacetophenone or parahydroxyacetophenone, then the yield was very poor. So now what we do is we use a special reaction for this, which is Fries rearrangement. What is done in Fries rearrangement is that phenyl esters are heated with anhydrous aluminium trichloride when we get ortho and parahydroxy ketones or a mixture of both. So what we see here is that when we do the reaction at low temperature, then we get parahydroxyacetophenone, and when this reaction is done at high temperature, then we get a orthohydroxyacetophenone. So this is an example. This reaction can proceed either by intermolecular hydrogen bonding or intramolecular hydrogen bonding, and it is an example of electrophilic substitution reactions. First, we will go into the mechanism of intramolecular hydrogen bonding in detail. So what we find in intramolecular hydrogen bonding is, in first step, this aluminium trichloride reacts with this oxygen to form a complex. Now this complex breaks down to give us this acetyl carbocation, that is acyl carbocation, which then acts as a electrophile. And from here, then the reaction mechanism is just like FRIEDEL-CRAFTS acylation, that is, it will go and react at the ortho position, that in this case the pi electrons here are acting as nucleophiles, and this will go and attack at the electrophilic site here, and we get a complex here. Now in this step, what happens is a Cl from here and a hydrogen from here will be eliminated. First of all, this is resonance stabilized, and then what we find in the next step is that this hydrogen and this Cl from here is eliminated. These electrons go back into the ring to regenerate the aromatic system, and we get this complex. This on hydrolysis will give us a orthohydroxyacetophenone, and then the similar reaction can take place at the para position also. Now if we talk of the intramolecular rearrangement, then what happens in intramolecular rearrangement, that this AlCl3 again reacts with the oxygen here to form a complex. Then in this case, this does not break from here as we had done in intermolecular hydrogen bonding. In intermolecular rearrangement, this was breaking from here to generate a psyllium ion which was acting as a electrophile. What happens in this case is that these electrons from here act as nucleophile and there a bond is formed here with this carbon, which is the electrophilic site here, and the migration takes place and these electrons from here go from here to, and this positive charge is removed and we get this intermediate here. This is similar to what we were getting in third step of the intermolecular rearrangement. Then in this case again HCl is removed, hydrogen is removed from here in form of HCl, which regenerates the aromatic system. Now when we bring about the hydrolysis of this, we get orthohydroxyphenol. Please remember, now if we look into this structure, then what we find is that this structure orthohydroxyacetophenone is stabilized because of chelation, that is because of intramolecular hydrogen bonding. So what we find is that when we do the reaction at low temperature, then the para product is the major product, because there the reaction is kinetically controlled, that is it follows along that pathway where the energy of activation is lowest. Whereas at high temperature, ortho product is the major product because of chelation. So now what we know is that we cannot prepare orthohydroxyacetophenone by acylation, but we can prepare orthohydroxyacetophenone by special reaction which is Frie's rearrangement. So for that what we will have to do is, we will have to convert first phenol into its ester, methyl phenyl ester, and then do the reaction with AlCl3 when we get the orthohydroxy and parahydroxyacetophenols in high yield. The next reaction which is of interest is CLAISEN rearrangement reaction. In CLAISEN rearrangement reaction, aryl-allyl ethers undergo intramolecular rearrangement to form allylic phenol. So what we find here is that this allyl phenyl ether undergoes intramolecular rearrangement to give us a orthoallyl phenol. So what we find is that this reaction in this, when this group, allyl group, migrates from here to this position, the ortho position, here also a allylic shift takes place. Along with ortho, allylic shift is also taking place here. And what we find is the ortho product is the major product. This is an example of intramolecular rearrangement. So what happens is, in this case, this bond breaks from here. It involves the sigma bonds as well as there is a pi rearrangement. This bond breaks from here and this comes here. So what we find here is, in this case, the alpha carbon which is here, it will become the gamma carbon in this case. So this is the reaction mechanism, or we can say, so now what we find here is, if we look here, first thing we will get only the ortho product. Second, in case the two of the ortho positions are blocked, then in that case we will get the para product. And please remember, when we talk of the ortho rearrangement, then in that case the allylic rearrangement takes place. That is, the alpha carbon which is alpha here, that becomes gamma in the product, and one which is gamma there, that becomes alpha in the product here. Whereas when we talk of the para rearrangement, intramolecular rearrangement, no such rearrangement is possible, that is alpha stays alpha and the gamma carbon stays the gamma. The second point that we have to keep in mind is that if both ortho and para positions are blocked, then no reaction takes place at the meta position. Now we know that this reaction is a intramolecular reaction. How can we prove that? That is, if we take two different ethers, like one is this ether, allyl phenyl ether, and another one is substituted allyl phenyl ether. Now when we do the products, when we look into the product, then what we find is no cross products are being formed here. Since no cross products are being formed, we will say this is a intramolecular reaction which proceeds in a concerted manner. Now what I mean by saying is it is a concerted manner. This mechanism can also be proved if we take this carbon, we labeled carbon with C14. What we mean here by saying is a concerted manner is this bond cleavage here and this bond formation here takes place simultaneously. So this involves 2 sigma bonds, and this is an example of pericyclic reaction which involves sigmatropic rearrangements. Not only this, what we will find is that there is rearrangement of the pi system also. So when we have this rearrangement, so we get a cyclic intermediate here in which the bond cleavage from here and the bond formation here is taking place simultaneously, resulting into this. So what we find here is that there is, along with the reaction at the ortho position, a allylic shift is also taking place, that this alpha carbon here, which was alpha to this oxygen, is becoming gamma to this carbon in the product. So here allylic shift is taking place. So what we get here is we get this reaction, that is the bond formation here and the bond cleavage here. So bond cleavage is taking place between oxygen and the carbon, between that carbon and oxygen, which is alpha, and bond formation here is taking place between that carbon, which is gamma, and the carbon of the ring. And what we find here is that what we get here is cyclohexadiene enon. So when we get cyclohexadiene enon, the next step is the fast step, because this enon changes into the ketonic form, into the enolic form, which is the phenolic, which is more stable. So what we find here is that this reaction is an intramolecular rearrangement, and if we look into the ortho mechanism, then what we find is that along with the reaction taking place at ortho position, allylic shift, allylic rearrangement is also taking place. That is, allylic shift is taking place and an allylic rearrangement is taking place. Whereas if we talk of the para product, that is, if both the ortho positions are blocked, then what we find here is the first rearrangement is the same, that the bond cleaves from here and a bond is being simultaneously formed here, and we get this position here, this here. So there what we find is, so the first inversion has taken place, that is the alpha carbon has become the gamma and gamma in the this. But what happens, this is the first inversion, please keep this in mind, but we do not have a hydrogen here. So this cannot go back to the enolic form. So what happens, we know that enolic form is more stable than the ketonic form here. So the second inversion takes place here. Now in second inversion, the same thing happens, that is the rearrangement here takes place through the bond here breaks through the, is forming here with the gamma carbon, and here the bond is breaking between the alpha, and we get the second product here. Now this, in this case, now the prototropic, that is the proton comes here, that change takes place here, and we get here the enolic form. So in para migration, no allylic change is taking place. The carbon which was alpha to the to the oxygen originally becomes alpha in the product also. So what we see here is, in CLAISEN rearrangement is an example of a pericyclic reaction which involves a sigmatropic rearrangement. One sigma bond changes to another sigma bond in an intramolecular process, and there is no involvement of catalyst. We do not need a catalyst in this reaction. And then a substituent moves from one part of a pi bonded system to another point in an intramolecular reaction with simultaneous rearrangement of pi system. These were some very interesting reactions of rearrangements. Now we will go on to some important synthetic reactions. The first one being the KOLBE-SCHMIDT reaction. This reaction involves the interaction of phenol with carbon dioxide in presence of sodium hydroxide at high temperature under pressure. Please remember, carbon dioxide is a weak electrophile. So again, in this case, what we need to do is, we need to dissolve phenol in aqueous sodium hydroxide. When we do that, phenol is converted to sodium phenooxide, in which case phenooxide ion acts as an electrophile and it reacts with the C of the carbon dioxide to give us sodium salicylate. And if we do this, which on hydrolysis then gives us salicylic acid, orthohydroxybenzoic acid, which is salicylic acid, and para-hydroxybenzoic acid. So what happens is, at low temperature, orthoisomer predominates, where at high temperature, it is the para form which is formed as the major product. So here again, what we've shown here is the mechanism of the reaction, that the phenooxide ion is acting as a nucleophile. It is reacting with a carbon here, which is the electrophile, to give us this intermediate, in which this proton is removed here to give us a aromatic system. And this salicylate ion then undergoes protonation to give us salicylic acid. Now in our next lecture, we shall be discussing the synthetic uses or industrial uses of salicylic acid. Thank you.
Dear friends, on that note, we would like to thank Dr. Chauhan for coming to our show and delivering this wonderful lecture. With this lecture, we hope that you have come to understand the concept of phenol and its acidity and its chemical reactions. On that note, thank you, dear friends, for watching our lecture. Stay tuned and keep watching. Thank you.